I'm going to present my project about trajectory planning using manipulability maximization and control minimization. Trajectory planning is a key task for robots to move from a place to another. For mobile manipulators, it's quite easier because they are mainly in 2D space. However, for robot arms, it's quite challenging not only because they are in 3D, but also they have multiple joints. And also unoptimized controllers or planners can cause serious problems. Recently, people have worked on the control level to solve failures caused by singular Jacobian matrices, and they try to find the optimal configuration with the highest manipulability index. So in this project, I would like to apply this idea to planner and to plan a trajectory with high manipulability and low control cost to be energy efficient. So I'm first going to implement the idea and then apply it to optimize the planner. Given the new configuration, the non-optimized controller simply uses inverse kinematics to calculate the control and use the control to update the configuration. To solve the optimization problem, we can simply use fmin_con to find the optimal configuration with the highest manipulability index. Now let's work on the planning. For quick setup, we assume there's no advanced task, and our naive planner simply generates a straight line in 3D space. To optimize the planning, let's first recall our goal is to maximize the manipulability measure and also to minimize the control cost. So this is our new objective function, where the alpha is a trade-off ratio representing how much we care about the manipulability maximization. And I chose to use trapezoid method for integration, and the optimization problem can be solved by this library. For simulation, I chose to use KUKA 14, KUKA UR14, an industrial robot arm with 7 joints. So here is the simulation with naive planning and non-optimized controller. The red dots are the planned and effector's positions, and the blue dots are the real positions after the control. And now it's running with optimized controller. We can see from this table that with the optimized controller, we can always get the higher manipulability measures. Similarly, let's run the optimized planning. First with non-optimized controller, and now with optimized controller. We can see the manipulation process this time is much faster. This is because the positions given by the optimized planner are easier to reach. And from this table here, we can also see no matter what alpha is, the optimized controller can always give us the higher manipulability index. To find out the relationship between the manipulability and the trade-off parameter, I construct this graph from the previous plot. And we can see when alpha is 0.5, we can get the relatively highest measures. So 0.5 could be used as a potential trade-off value for our twinned offline planning algorithm. So in this project, I have shown that maximizing manipulability is effective in both planning and control. And I also developed an energy efficient planning algorithm which outputs positions to let the robot arms to have higher redundancy. And my parameter tuning and selection in this work were very rough due to the lack of time, and they could be replaced with advanced machine learning methods. And the planning algorithm could also be advanced by adding new features. That's the end of my presentation, and thank you very much.